Hi, this is Mark Kemper with EMS, and in this video, we are going to 3D scan, reverse engineer and CAD model, and generate an inspection report on a real part. So what do I mean by a real part? Well, if you go out on the internet, you see a lot of people doing demos and they're scanning widgets and statues and all kinds of stuff that companies that are doing manufacturing or design, they're not doing that kind of stuff. And the other thing is, most of them just show the scanning, they don't show the modeling or generating an inspection report. So what I want to do today is I want to show the entire process, and we're going to do it on this part. And I call this a real part because this is out of a Jeep. It's a steering knuckle. And it's got some prismatic shapes, but then it has a lot of free-flowing organic shapes, and those have to blend into some of these planes and cylinders and so forth. So it's actually a pretty tricky part to model. And we're going to show you how to model this entire thing as a sketch-driven, feature-based, solid model, and then we're going to generate an inspection report with full GD&T. Now, the other thing to make this even more complicated is we're going to change the manufacturing process. What do I mean by that? This part was forged or cast. We're going to CNC machine our part. So we got to change up some of the things as we reverse engineer this part. So that adds another layer of complexity to it. But we're going to walk you through and show you what it takes to go from scan to CAD to inspection. And we're going to take you through that entire process. So starting with the 3D scanning itself, we're going to use the Creaform HandyScan Black, but there are a lot of scanners you could use for this, for a part like this. We're going to use the HandyScan Black because of the accuracy it provides and the ability to do dark and shiny surfaces on something like this. And we're not going to spend a lot of time on the scanning because we have lots of videos that show scanning, show this scanner in detail and other things. But let's just go ahead and start and get this scanning going. I'm using this little Lazy Susan or rotary table that allows me to move around the part. All scanners or most scanners are line of sight. So we're just going to move around and get as much of this. And then when we're done, we'll flip the part over. The little yellow triangles are just there. This scanner requires targets, so as I lean down, it still has targets to see, but there's also targets on the table itself. But you can see it doesn't take long to scan this part. It has this single line mode that allows us to get down into some of these smaller holes, and then I can switch back to the 22 line mode at any time. This is blue laser technology, so as I mentioned, very good on dark and shiny. And this scanner has a very good ISO certified accuracy. And again, if you want to see a lot of detail on this scanner, we have some great videos. But you can see the scanning does not take long on a part like this. That's pretty good. Now what I'm going to do is stop scanning. We're going to flip the part over and then scan the other side. So, and these triangles just kind of help hold the part from moving around. We don't want it to move around because we have no targets on this part. We've just got targets around the part. So then we come over here in the software and we just tell it we are going to add another scan. We do not want to copy the positioning targets because some of them got moved around a little bit. We hit start scan and off we go. Okay, and we'll get this side. And you can see there's some decent complexity on this part, especially on the other side. There's a lot of organic surfaces, but even on this side we've got some shape to it, because these parts are typically cast or forged and then machined. So there are some critical, surfaces, especially all the machined ones. We want to make sure we get those really well and then get into, again, any of these holes in that single line mode. That's just going to be able to scan down in there deeper, especially the smaller they get. But you can see, in a matter of a few minutes, we can scan this part. It's not difficult to scan, and that's the thing. These scanners nowadays are getting so fast and so good and so accurate that scanning has really become a very small percentage of a project. It might be now 10 or 20% of the project. The real work is in the modeling and generating the inspection reports. So a part like this, which we're going to show the modeling next, is really where the work is. And then same for the inspection. Are you just doing a basic first article, or are you doing a very detailed inspection and have lots and lots of call-outs? That's where the real work is, and that's what we're going to get into next. But we'll show you how to clean up this scan data, put the two halves together, because we've done it in two separate scans. We'll show that next, but then we're going to really focus on what does it take to turn this into a feature-based solid model that I can then use for downstream manufacturing applications.
All right, so here in the Creaform software, the first thing I want to do, you can see our part here. First thing I want to do is get rid of kind of all of the data we don't need. There's a command in here called remove background that basically finds the table, basically the flat surface, and it's going to create a clipping plane and clip that off. Okay? And now what I'm going to do is I'm just going to now select the part itself, invert the selection, and then delete all the rest of the data. And now we can get rid of that clipping plane. We don't need it anywhere. That's just anymore. That's just a quick way to get rid of a lot of the data. And let's go to the other scan. We've already created that clipping plane. So let's go ahead and select this, invert the selection, delete all that data. And then we'll also get rid of that clipping plane. So now we have the two sides. So what we want to do is align them and then merge them. And it could be two sides, it could be 3, 4. I mean, it just kind of depends on how many sets of data. Typically it's a couple, but sometimes we have to do 2 or 3 depending on the part. So I'm going to use the manual method, and what you do is you just kind of put them in the same orientation, and then you pick some points on each one. They just have to be close, and that just gives the software a head start, gets them fairly closely aligned. Now you do a best fit. It's going to go in there and really figure it out. You can see now we have a nice overlap between these two, and then we hit merge, and it's going to merge all that scan data together. So again, the time to scan and manipulate this data and get it to a point where it's ready to model it does not take very long on a part like this. It's just a matter of a few minutes. And let's hide the original one there, and let's just hide our positioning target. So you can see we got very nice looking data. Only took us a few minutes, and this is about all we need. We're ready to go for the next step, which is the actual modeling. So let's start by showing the 3D scan data, and then we're going to overlay the final CAD model we created. But as you can see, there's some real complexity to this part. And here in blue now is the final CAD model that we're going to show you how we create it. Back to the scan data, again, just to show the two models and how they compare to each other, so you can really see the complexity of the part on this side. Again, the final CAD model, feature-based solid model of this part, and then finally back to the scan data, just so you can see them over top each other. And we're going to go into detail on how we did this modeling. All right, so let's get started here. Now, I am in Geomagic Design X, and this product is specifically designed for reverse engineering of 3D scan data. It's very similar to a SolidWorks or a CATIA or an Inventor or a Siemens NX. It does both, sketch-driven, feature-based solid modeling and surfacing. The biggest difference is it has this front end to work with scan data, because scan data, as you see here, is nothing more than triangles, okay? Basically STL data. So if you zoom in, you can see what this is. It's just triangles, okay? So it's a very stupid model. It has no intelligence to it, okay? Now, the first thing I'm going to do is I'm going to show you the wrong way to design this part, because we see a lot of videos and demos out there, and a part like this where you have some very organic shape, but then yet have prismatic shapes, there's a certain way people tend to model those, and they do it that way because it's fast and easy, but in our opinion, it's the wrong way to do it, okay? So if you look at this part is either cast or forged, and it's pretty obvious because you can see parting line, All the walls have draft to them. You can see like tooling marks. Maybe the tool's worn out in certain areas. You can see imperfections. We've got a probably a part number on here. This is probably where the riser or the gate or a sprue was cut off in the post-processing. So this part is cast, and then they'll machine in the holes and some flat surfaces. So, fairly typical, okay? So what I'm going to do is I'm going to roll back in the tree back to this point here, okay? And I want to show you how most people would model this, okay? So we're going to roll back, and what they tend to do, let's turn on another copy of the mesh, and you'll notice something different right away. All the holes have been removed and it's been filled in, okay? This is still scan data, okay? But a copy was made and the holes and the sharp corners were taken out. So for example, let's turn back on that raw scan data and then this modified version of the STL file. So what they'll do is they'll make it like this, and then what they would do is auto surface it. And let's turn the mesh off. Okay, so if you look at this, we now have, instead of 3-sided triangles, we have 4-sided surface patches. You look over here in the tree and it says it's a solid body. It is technically now a CAD model. This is a solid body. But there's no associated sketches or other items here. This is just one big, dumb solid, okay? So yes, in a sense, it's better than just an STL file because I could export this now as a STEP or, IGES or Parasolid model. But again, there's no intelligence. If I want to come in and, change this surface shape here or take the draft out, you can still even see like the parting line. Let's turn off the edges here so you can see it, okay? So again, bring the mesh back, turn it off. It's pretty much an exact replica. And when we reverse engineer something, we typically don't want to, we're scanning a manufactured model, but we want to reverse engineer back to the design intent, the original design. And that design probably didn't have the draft in it, didn't have the parting line, didn't have the tool marks, didn't have, the cutoff and that kind of stuff. It was a CAD model. Because if you're going to go and get this, manufactured again, maybe you're changing your process. In our case, we're going to CNC machine this out of billet. We're going to make some modifications to the design a little bit. So we don't want draft on there. We don't want parting lines. We don't want all these imperfections in the model. And if we're going to make changes to it, it's going to be very difficult using this modeling method. So let's just carry on through the tree a little bit here just to kind of show you. And I'll just roll forward a bit and you can see what this process would look like as we continue through it. So you can see they basically would create cylinders or sketches. So there is a few sketches in here, and then they're going to, Boolean or cut those out. And let's just roll all the way to the end, okay? And then this will be what the final model looks like. So just really adding in the holes and everything. So again, let's turn back on our mesh. Let's go back to the original mesh, okay? And you can look at it. And the blue is the mesh, and the gray is the final CAD model, okay? So you'd look at that and say, yeah, that's great. That's a perfect replica of the model. But that's not what most people want. This model, other than the holes and a few flat surfaces, there isn't much to edit here, okay? And if you look at the whole process, we have about 12 features, 12 sketches on here. So, you could model this in a few hours. But again, the problem is if you send this to somebody and then they want to make changes to it, you really can't, okay? So in our opinion, this is the wrong way to model, but a lot of people do this because it's fast and easy, but you're really limited, and quite frankly, it's still the manufactured part. It's not the design intent, the as designed. And even if you were to, let's say, sandcast this again, you could send this to 2 different manufacturers, and they may have 2 different methods of creating the parting line and setting up this part, but you've kind of already, baked that into here in because it's to whatever the original process was. So again, this is, in our opinion, the wrong way to do the part. So now let's show the right way to model the part. So here is the finished model done more of the traditional sketch-driven, surface-driven, history tree modeling as you see here. And you'll notice right away big differences, okay? Let's roll this over so you can kind of see it. So still, looks pretty much like the original or the scan data with some differences. So let's bring on the scan data. So right away you'll notice we don't have parting lines. We have straight walls in here. We have everything is, driven by sketches, okay? So let's roll this over and you can see it. Now, a couple things. One, all the holes and all the critical surfaces are, right on. And then some of the surfaces we made, for example, this surface here, it still has the curve, but we made it nice and smooth. Same with here. I mean, we probably have to follow, our limits to where this has to fit in the vehicle and how much clearance we have. But we can smooth these surfaces out. We can make things the right way. We've taken out, so again, let's turn off that scan data. We've taken out, for example, the part number. We had the kind of where this part was cut off here. All those imperfections are gone. And everything now is sketch driven. So let's walk through. I'm going to just do a real quick walkthrough of this part as far as all the features, and then we'll go into a little more detail. But I want to start by just showing you all the features and what it took to model this part. So what I'm doing is just stepping through the tree, and this will kind of just highlight all the sketches that were created to build this. So as you can see, it's a lot more involved. So instead of going from a few hours to model this could potentially take a few days to model it. But what you end up with is a full-blown history tree with every feature associated to a sketch that you can roll back and make edits to. So if you don't like a certain feature, you can go back to that sketch, make a change to that sketch, and it updates the model. And in our opinion, this is the correct way to do it. So instead of having 12 sketches, we ended up with over 50 different sketches or steps, we can call them, in this model. So yes, it took a lot more time, but it's the right way to do it. Because we get calls from people, or we talk to people that have had 3D scanning done in the past, and they haven't necessarily been happy when they're doing a part like this. And that's because somebody did the first method that we showed, and they send that to the customer, and of course they want to make changes to it or change it for a different process, and they basically end up with a model that they really can't do anything with, and it's full of all the manufacturing information, draft, parting lines, things like that, tooling marks like we've talked about, and they can't take those out. They can't really edit the model. So this kind of looks like spaghetti, but you get the idea. This is what it takes to model something like this correct. And as I said, this could take a few days to do, but this is the right way to do it. So we'll break it down a little more and actually show you step by step, how we end up with this final CAD model, and it'll look better than just kind of this spaghetti on the screen. So to set up what you're looking at here is we have a top and bottom view of the part, and what I've done is just done a screen grab at different stages as we go along. So you can see the first sketch here we've built, and then we're going to extrude it. And there's really two ways to build models. You kind of build up or kind of tear down. And for this part, tear down is the way to go. So we kind of make the major shape, and then we're going to start chipping away at it and cutting it back just because of the shape of the part. So the circle, their cylinder in the middle there is pretty straightforward. And then we're going to cut sections or do mesh fit surfaces and then extrude up blocks and then cut them away. So you can see I've got some all these organic surfaces. I'm fitting surfaces through those areas, trimming those surfaces, and then extruding it up and then cutting that block away. So you can see I'm doing all of the really organic curved areas first and making sure they all blend together, and then we'll start working on some of the other stuff. So it takes a little bit of work, to do each one of these steps. And as we mentioned, there's about 54 steps or so in this whole process to do this. But we found for this part the best way to do it. But you can see I'm making my walls vertical. I've got nice smooth flowing surfaces, And of course, I can control all of this by going back and either editing those sketches or even editing those surfaces I'm building. So I have a lot more control of this model. Plus, I have the ability to make changes or to omit things that I don't want or need in the model. So I have much more control, and I can go back to the design intent of the original model, even though I've scanned the manufactured part. Again, I will make sure the key machine surfaces and holes are very accurate, but then I have much more liberty on the rest of the part. I probably can't deviate too much because we have space claim requirements in there or limitations, so we got to stay pretty close. You can see here I'm adding in all the fillets and doing some of the final steps here, but this gives you an idea. Then we run the accuracy analyzer to compare it back to whatever tolerance we want to the scan data. You'll see some slight differences, but we're okay with those because they don't really, again, affect everything. And so there's the final model here. We'll spin this around so you can see it, but you can see it's a much better looking model. It looks more like a CAD model. And we have a lot of editing capability if we do want to go back and make changes, but we can export this now in any CAD format. So our next step is to send this out to get CNC machined from billet material, because again, we have changed our manufacturing process. Now, once the vendor gets the part machined, they're going to send it back to us. We're going to scan the part again, and then we're going to compare it to the original CAD model. So this will be our first article. We want to make sure it's right before they machine a whole bunch of parts. So we're going to show you how to set up and inspect a part from 3D scan data. All right, so we've scanned the part again, and here now we are in Polyworks, and this is what we're going to use for the inspection. Polyworks is a very powerful inspection tool used heavily in automotive and aerospace. So the first thing we do is bring in the CAD model that we built from the scan data. We'll import that in. And then once that comes in, we are going to import the scan data. And again, this is the new scan data. We've got the CNC part back that was machined. We've 3D scanned it again, and we're going to import it. Now, first thing you notice is they're not in the same coordinate system, because whenever we scan something, it's not in a coordinate system. So we're going to do a quick alignment or a best fit, and that'll just get them on top of each other. And theoretically, they're now aligned. But for most machining parts, they use a datum alignment system. And this goes back to the days of the CMM world, where you had to fixture a part down, and typically you'd have an ABC datum. Your A datum is usually your primary, your most important datum, followed by B, your secondary, and then C. And you're basically locking the part down so that it can be fixtured, and then you inspect in that datum alignment. But theoretically, you could use best fit, and there's lots of other alignments. Now, our 3 holes on the bottom are the most critical mounting point, so that's going to be datum A. So we're going to want to make sure that we lock down datum A, and it's actually going to shift the scan data and prioritize datum A. So it's going to match up that scan data as closely as it can to that bottom datum. Then the second one will be this side here, and we'll call that datum B, the side of this kind of arm sticking out. So that's going to lock down one of the other axes. And then finally, this hole in the back will be our third datum, and that's going to lock down the third axis, so to speak, and position it. So we're just telling it we're going to use the circle center, and we're going to create our datum, and then actually tell it to now align to that datum. And if you don't know much about datum alignments, there's plenty of videos out there. Same with GD&T. We're going to show a lot of GD&T, and if you're not familiar with it, there's lots of videos on what is GD&T and how it works. But it's basically a pretty commonly used measurement system for a lot of manufactured parts. Okay. So there we've actually going to do the datum alignment. So we're going to pick the references. So again, feature A, feature B, or datum A, B, and C. And we're going to tell it now to actually move the scan data to align to that. So that's what we have here. And then once we have that, you can see the values from that alignment. And there's our mesh, so you can see how it kind of lines up on there, okay? So again, priority will be that bottom. Now the next thing we're going to do is a quick just color map, heat map people call it, color deviation map. This isn't something you can really quantify with real measurements. I mean, you kind of can, but it's really just a quick look at the part. We can adjust the tolerance range, and basically, so we can just do a quick look at this part and see, hey, are there any issues, right? So we set a tolerance, and everything in green should be in that tolerance. But if you look at this top surface here, it's approaching yellow. So at least that's telling us, hey, there might be a problem. We can see some other problems. Now, some of these problems may not be in critical areas. We may not care. But if you notice that one hole there in the back, that's yellow, and we should not have that. So at least we know with this quick check in this datum alignment, we may have some issues. Once we get in the GD&T, we can further explore that and validate if there's issues. But the color map is a nice quick kind of go, no-go check. If we saw like a ton of red, then we'd know, maybe the whole part is out. So that's just something to be aware of. All right, so now we're ready to actually start putting in some of our GD&T information. And the first step is to define the geometry that you want to then apply GD&T to. So the first thing we want to check is the holes. Those are some of the most critical surfaces on a part like this. So we're going to pick all of the holes, or cylinders really, as you see here. We're going to pick all those to define them, and then we're going to apply various different GD&T callouts to all of these holes, because again, these are usually some of the most critical items. If these holes are not in the right position, or they're not round, or not cylinders, you could have issues. So once we pick them, what we'll end up doing here is telling it what tolerance, and you may have different tolerances on different holes. So the first call out we'll do is positional tolerance. That's one of the most critical ones. Is the center of the hole even in the right spot? So we're going to pick these first three, this bolt hole pattern at the top. That's one of the most critical, and we'll define its position. And the tolerance on this one, we're going to set at 0.05. Now keep in mind we are in millimeters, so that's 50 microns, or about 2/1000ths of an inch. Okay, so we'll define that. You can define it as a bolt pattern or bolt circle as well, and we'll define some of the other ones here. Now this starts to become a little bit repetitious, so we'll let some of this run here at normal speed, but then we'll speed it up. So we're going to define all the positional tolerances first, like I said, and they may have different amounts, different tolerances. You can see here this one's 0.1 or 100 microns, or about 0.004 of an inch. Now, what determines these tolerance amounts and different GD&T items we're adding on? Well, it's really either the designer or the machinist, or a combination of, but somebody who understands manufacturing and also understands how this part is being assembled with other parts, and what is critical and what is not. You don't want to over-constrain have a super tight tolerance on something that really doesn't matter, and at the same time you don't want a low tolerance. So we're going to show positional tolerance. Then we're going to check cylindricity. That's looking at it as a 3D cylinder. Is it truly round all the way through the part? We can also check concentricity. That's where two of these holes have to line up perfectly with each other. We're going to pull some dimensional measurements from one side or one plane to another. We want to check the measurement between a couple of the holes on here. So we basically just go through and assign the different callouts, put in the values, typically the tolerance, to it, and then we're going to run a report and take a look at it. Okay, so it gets a little bit repetitious, but even a simple part like this could have 50 callouts on it, again depending on how many features are on here and how critical they are. But certainly all the holes, or most of the holes, are critical. some of the faces from one side to the other, the machine faces on this kind of main hub, they have to be accurate. Some of the other faces fit in with other they slot into other things. So again, they have to be within a tolerance as well. So that's the general idea. And general rule of thumb is each call out takes about a minute. So if you had 50 call outs on a part, you'd be looking at roughly an hour. We've done parts with hundreds of call outs on them, and very advanced datum alignments, multiple datum alignments, very complicated alignment systems. So you could spend a day just building the inspection report. Now the good thing is, once you build this report, you don't have to build it again. So for example, maybe we got 10 of these parts, first articles from the machine shop that we worked with. So we said, hey, give us a short run of 10. Once we build this report, then we just have to scan each part and then load it in and run the report again. So we don't have to rebuild this. So you kind of create the recipe to start, and then you can just, assuming it's the same part, you just scan each one. You save that scan file as a different name, and you can actually batch process, have it load each one in automatically, generate the inspection report, and spit out the results. That can be all done with a push button. But you definitely have work up front to build the report like you see here. It does take some work, and it takes some knowledge to understand GD&T and manufacturing processes and how parts assemble together. Because if this part is off, theoretically, everything attaches to it, it's going to affect it. So it's critical that we get a part where these key dimensions or these key callouts are, these key locations and key dimensions, that they are within the tolerance that we have specified with the CAD file and the drawing we sent over to the CNC shop. Now let's go ahead and take a look at our actual inspection report. So now that we've created all of those GD&T callouts and measurements, we've spit it out into a report. This can be exported in PDF and an Excel spreadsheet and other formats. So here's our part here, just some basic information. And here's that color map. Again, doesn't tell us a whole lot other than we see some areas of concern. Here's a couple different views of it, just to kind of highlight it and again show maybe some areas of concern. Here is our datum alignment. So if you look at our datums, they all lock down pretty well. So we know we've got a good lockdown of our datum. We're not seeing numbers real far out. So if one of these wasn't a plane or wasn't a good plane or something like that, you'd see it. But our scan data did lock down to that datum real well. Here is all of our positional tolerances, and we can see some of these have failed. Cylinder 2 over here on our bolt pattern, this cylinder here, E. So, and you look at these numbers based on the tolerance we gave it, some of these fail pretty spectacularly. This one's off by a millimeter. This one's off by 360 microns. This one's off by 124 microns. So we definitely have some issues with some of our holes. This is our cylindricity. Same thing, that datum, that cylinder E, not only is the positional tolerance wrong, but the hole is not round. It's out of round by 196 microns. So definitely have an issue with that hole. Next up, this is our overall dimension from this top surface to the bottom surface, and we kind of saw that in our color map. That is off by 1/4 millimeter. And if that's a critical dimension, obviously we have problems here. Next up, we have some parallelism. So this plane here and the plane on the other side are supposed to be parallel. They're not. So one of those is probably on a wrong angle. And again, if this has to mate or slot in to two other flanges on both sides, it may not fit well. This one does as well have to slot in somewhere. And you can see that one is fine. These are, now what we did here, because this is actually has a taper like a cone, so we cut a series of sections through it. So our top looks okay, but our bottom area down here where this flange is, we've got some real issues. So there's a challenge on this main hub. Finally, we've got a flatness call out on the top here. That looks good. And then we did a couple surface profiles. Those aren't really critical, but it just looks at those organic surfaces and says, hey, does the scan data fit within, we said 0.1 millimeters, and it does. So that's fine. Nothing to worry about there. And then another key measurement is concentricity. So this hole here and this hole here have to be basically on the same axis, and they're not. Well, we know that hole, one of these holes, datum E, is got some real problems, so I wouldn't be surprised that this failed. So so that's it. So that's our inspection report. We would send this back to the machine shop and say, hey, these parts do not pass. We have some real problems, and probably in their fixturing and their setup, something didn't go right because this part has to be machined in multiple setups. So they're going to have to go back and correct the problem. But you want to find this now before you order 100, or 1,000 of these parts. So that's why we want to do a quick scan and inspect of this and compare it back to our final CAD model.
So this concludes our video on 3D scanning, CAD modeling, and inspection report generation on a real part. As I mentioned earlier, you can go out on the internet and you see a lot of videos of people scanning statues and widgets and people and other things, but that's just not the real world. Manufacturers need to scan and model parts like this. And again, it's not a very big part, but it's got some real complexity in these organic surfaces and just the shape to this. And hopefully you found it helpful to see what the real process looks like. Because honestly, nowadays, these scanners are so good that that's 10%, 20% of the project. The real work is in the modeling, in the inspection report generation. In our case, not only did we have to reverse engineer it, but we're changing the manufacturing process. And we want to get back to a sketch-driven, feature-based, solid model that is editable. And that is not easy to do, as you saw. Same with the inspection report. You want full GD&T? Are you just trying to do a first article with a handful of critical dimensions? Or are you trying to call out everything? Do you have some complex call outs, datum alignments, things like that? So hopefully this sheds some light on what it takes to scan a part, model it, and generate an inspection report, again, showing the entire process.